welcome to G Fun Facts Online. Today, we're diving into a quiet revolution happening not in factories with gears and levers, but deep within the atomic heart of matter. It's a revolution that promises to completely reshape our technology, and it's being led by a class of substances called quantum materials. These aren't your everyday materials. Their properties are governed by the strange and counterintuitive laws of quantum mechanics. Think of electrons being in multiple places at once, or tunneling through solid barriers. In most materials, these weird effects get washed out. But in quantum materials, they take center stage, creating behaviors that have no parallel in our classical world. At the heart of this revolution are chemists, acting as modern-day alchemists. They are the artisans learning to craft and control these materials, unlocking their potential to forge a new generation of electronics. We're going to explore how they build these materials atom by atom, how they tune their extraordinary properties, and what it all means for our future, from computers that are millions of times more powerful to power grids that lose zero energy. Let's explore the alchemist's touch and see how chemistry is forging the future of electronics. The journey to creating a functional quantum material starts with its synthesis. The precise arrangement of atoms in a crystal lattice is everything. It's the foundation upon which all the exotic electronic properties are built. Even the slightest imperfection, a single atom out of place, can disrupt the delicate quantum states that make these materials so special. So the first and most critical challenge is to synthesize incredibly high-quality, single crystal materials. Chemists have developed a sophisticated arsenal of techniques to achieve this atomic-level control. For many modern electronics, materials are needed in the form of ultra-thin films, sometimes just a few atoms thick. Two of the most powerful techniques for creating these films are molecular beam epitaxy, or MBE, and chemical vapor deposition, or CVD. Imagine atomic-scale spray painting. That's essentially what molecular beam epitaxy is. Inside an ultra-high vacuum chamber, which is cleaner than a surgical suite, beams of individual atoms or molecules are aimed at a perfectly smooth, heated surface called a substrate. The atoms land on this surface and, under precisely controlled conditions, arrange themselves into a perfect crystalline lattice, almost like Lego bricks clicking into place. This technique offers exquisite control, allowing scientists to build up a material one atomic layer at a time. This precision lets us create what are called heterostructures, layered stacks of different quantum materials. By layering, say, a superconductor with a topological insulator, chemists can create entirely new quantum phenomena at the interface, phenomena that don't exist in either material on its own. MBE has been crucial for developing everything from advanced transistors to the topological materials we'll talk more about later. Then there's chemical vapor deposition, or CVD. This is the workhorse technique for producing large sheets of two-dimensional materials, most famously graphene, which is a single layer of carbon atoms. In a CVD reactor, special precursor gases containing the elements you need are flowed over a substrate at very high temperatures. The heat breaks down the gases, and the constituent atoms deposit onto the substrate, forming a thin, uniform film. By carefully tuning the temperature, pressure, and gas flow rates, chemists can precisely control the quality and properties of the material. The ability to grow large, perfect sheets of 2D materials like graphene is absolutely essential for ever integrating them into real-world electronic devices. While thin films are key for devices, the fundamental properties of new quantum materials are often first discovered in larger, bulk, single crystals. Growing these is often described as more of an art than a science. One elegant technique is the floating zone method. This is perfect for materials that melt at very high temperatures. You start with a polycrystalline rod of your material. You then use a focused lamp, or radio frequency coils, to create a very narrow molten zone in the rod. As you slowly move the rod through the heater, this molten zone travels along its length. Impurities prefer to stay in the liquid, so as the molten material recrystallizes behind the moving hot zone, it leaves behind a highly pure single crystal. Another common method is flux growth. This is for materials that might decompose before they even melt. Here, the ingredients for your desired crystal are dissolved in a molten salt, called a flux, much like dissolving sugar in hot water. The whole mixture is then cooled down very, very slowly. As it cools, the material becomes less soluble in the flux, and perfect crystals begin to form and grow. Finding the right flux recipe can take a lot of trial and error, but this method has been instrumental in discovering many high-temperature superconductors and exotic magnets. So, whether it's atomic spray painting, chemical vapor reactions, or growing crystals in a molten salt bath, the goal is the same: to create materials with a perfectly controlled atomic structure, laying a flawless foundation for the quantum world to reveal its secrets. But creating a perfect material is often just the beginning. The real magic of quantum material engineering lies in the ability to then tune and control its electronic properties. This is where chemists become true masters of the quantum realm. By making subtle changes to a material's chemical composition or structure, they can achieve incredible transformations, like flipping a material from an insulator to a superconductor or activating a hidden topological state. They have three main tuning knobs at their disposal: doping, defect engineering, and strain engineering. Let's start with doping. You've probably heard of doping in the context of silicon chips. It's the foundation of the entire semiconductor industry. It means intentionally introducing a tiny amount of impurity atoms into a crystal lattice. In quantum materials, this technique takes on an even more profound role. By swapping out a small fraction of atoms with atoms of a different element, chemists can add extra electrons or create holes, the absence of an electron. This can radically alter the material's behavior. The most dramatic example of this is inducing superconductivity. Many quantum materials in their pure, undoped state are actually insulators, but by doping them with just the right amount and type of charge carriers, they can be transformed into superconductors, materials that conduct electricity with absolutely zero resistance below a certain temperature. The iron-based superconductors are a perfect case study. The parent compounds are magnetic, but not superconducting. However, when chemists dope the material by replacing some iron atoms with cobalt, the magnetism is suppressed and spectacular superconductivity emerges. Doping literally rewrites the material's electronic rulebook to allow for superconductivity. The next tuning knob is defect engineering. Conventionally, we think of defects or imperfections in a crystal as a bad thing. But in the quantum world, sometimes a beautiful imperfection is exactly what you want. Defect engineering is the controlled introduction of specific defects to create or manipulate quantum phenomena. A defect could be a single missing atom, called a vacancy, or one atom substituted for another. These tiny flaws can create localized electronic states that act like traps, allowing us to hold and manipulate a single electron or a single photon. A stunning example is the creation of quantum emitters in materials like hexagonal boron nitride, or HBN. Pure HBN is a wide bandgap insulator. It doesn't interact with visible light. But if you deliberately create a specific defect, like swapping a nitrogen atom for a carbon atom, you create a tiny, localized spot in the material that can emit single photons of light, one at a time. These single photon emitters are the building blocks for future technologies like quantum communication and quantum computing. The third tuning knob is strain engineering. This is exactly what it sounds like: stretching or compressing a material. By physically deforming a material, you change the distances between its atoms. This, in turn, modifies its electronic structure and can be used to induce new phases of matter. Strain is especially powerful for 2D materials. Take a thin film of a topological insulator. If you stretch it, you can enhance its special conducting states. If you compress it, you can destroy those states and turn it into a regular insulator. This ability to reversibly control the material's properties with mechanical force opens the door to creating things like topological transistors that can be switched on and off with a physical push or pull. These three tuning knobs, doping, defects, and strain, give chemists a powerful way to sculpt the quantum landscape of materials. They are learning to program matter itself, opening up a world of possibilities for the future of electronics. So we've talked about how chemists build and tune these incredible materials. But what's the ultimate payoff? The novel phenomena that emerge from quantum materials are not just scientific curiosities. They are the building blocks of a new technological paradigm. Let's start with the most famous quantum phenomenon, superconductivity. The ability to conduct electricity with zero resistance and zero energy loss is a holy grail of science. The problem has always been temperature. Traditional superconductors only work at temperatures close to absolute zero, making them expensive and impractical for widespread use. The discovery of so-called high-temperature superconductors, which work above the boiling point of liquid nitrogen, was a major breakthrough. Today, the chemical engineering techniques we've discussed, especially doping, are at the forefront of the search for a room-temperature superconductor. The potential applications are staggering. Imagine a world with lossless power transmission, where the energy generated at a power plant reaches our homes with 100% efficiency. Imagine super powerful, compact magnets for next-generation MRI machines, high-speed maglev trains, and particle accelerators. Superconducting circuits are also a leading platform for building the quantum computers of the future. The next frontier is topological materials. Their defining feature is the existence of electronic states that are topologically protected. This means they are incredibly robust and immune to scattering from common impurities and defects that would disrupt current in a normal wire. The most famous examples are topological insulators. They are insulating on the inside, but their surfaces host special conducting channels. In these channels, an electron's spin, its intrinsic magnetic moment, is locked to its direction of motion. This unique property, called spin-momentum locking, is a dream for engineers looking to create a new class of electronics called spintronics. Spintronic devices would use the electron's spin, in addition to its charge, to store and process information, leading to computers that are far smaller, faster, and more energy efficient than anything we have today. Finally, there's the exotic world of quantum magnetism. In some quantum materials, the magnetic moments of the electrons, their tiny internal compass needles, can't settle into a simple, ordered pattern like in a fridge magnet. Instead, they enter a bizarre, highly entangled state called a quantum spin liquid. Here, the spins remain in a perpetually fluctuating, liquid-like state, even at absolute zero. Synthesizing materials that host this state is a huge challenge. But scientists have made progress with crystals like Herbert-Smithite, where the geometry of the atomic lattice frustrates any simple magnetic order. While still in early research, the massive quantum entanglement in these materials could one day be harnessed for quantum information processing. From zero-resistance electricity to defect-proof electronics and liquid-like magnetism, the fruits of this quantum harvest promise to redefine what's possible. The process of engineering these materials is a cycle of design, synthesis, and crucially, characterization. Scientists need incredibly powerful tools to see if they've made what they intended to make and to probe its unique properties. Two of the most important are angle-resolved photoemission spectroscopy, or ARPES, and scanning tunneling microscopy, or STM. ARPES is the most direct way to map a material's electronic landscape. It's based on the photoelectric effect. In an experiment, a beam of high-energy light is shown onto the material, which knocks electrons out. A detector then measures the energy and the angle of these escaping electrons. By working backward using the laws of physics, scientists can reconstruct the energy and momentum the electron had while it was inside the material. This allows them to draw a complete map of the electronic band structure. For studying topological insulators, RPS is the killer app. It can directly visualize the unique Dirac cone shape of the surface states, providing the smoking gun evidence that the material is indeed topological. Then there is scanning tunneling microscopy, or STM, which allows us to both see and move individual atoms. An STM works by scanning an atomically sharp metal tip over a surface. When the tip gets incredibly close, a quantum phenomenon called tunneling occurs, where electrons jump across the vacuum gap between the tip and the sample. This tunneling current is extremely sensitive to distance, allowing the STM to create a topographic map of the surface with atomic resolution. But STM can do more than just see atoms. It can also probe their electronic properties, mapping out how the electrons are behaving around a single atom or a specific defect. Even more incredibly, the STM tip can be used to pick up and move individual atoms on a surface, allowing scientists to build artificial structures, atom by atom. This is the ultimate in bottom-up manufacturing of quantum devices. Together, ARPES and STM provide a complete picture. ARPES gives the global electronic structure, while STM provides the local atomic scale view. These tools are essential for guiding the design and synthesis of new quantum materials. The field of quantum material engineering is still young, and significant challenges remain. Synthesizing these materials on a large scale is a major hurdle. Many of the most fascinating quantum effects still only appear at extremely low temperatures, limiting their practicality. And our theoretical understanding of how these complex materials work is still catching up to the experiments. But the road ahead is incredibly exciting. The integration of artificial intelligence and machine learning is poised to turbocharge the discovery process. AI algorithms can sift through vast databases of chemical combinations to predict new materials with desirable quantum properties. We're even seeing the development of AI robots, automated synthesis platforms that can work around the clock, fabricating and testing new materials, freeing up human scientists to focus on creative design. The ultimate goal is to usher in a new era of technology, more powerful, efficient, and sustainable. From quantum computers that can solve problems currently unsolvable, to a perfectly efficient global power grid, the applications are transformative. The journey will be long, but the alchemist's touch of chemistry, combined with physics and materials science, is lighting the path to a quantum future. This ability to understand and manipulate matter at its most fundamental level isn't just a scientific quest, it's the key to unlocking a world of possibilities that we are only just beginning to imagine.